Okay, Forces in Motion, Chapter 10. This is part 4. We're starting to deal now with motion in 2 dimensions. So the motion is not necessarily horizontal or vertical. It could be at some angle. This is just the very start of it, and we're dealing here with forces that are represented as vectors. I'm just going to go through the 2 examples, example 8 and example 9. In part 4 of chapter 10 of the textbook. So in example 8, we have a resultant force of 3I plus 8J. So not to scale, this is the force 3I plus 8J. There's my object. It has a mass of 0.5 kilograms. If you wanted to draw that as an arrow downwards, that's fine, but in this context you don't actually need it for this particular example. We'll be needing it later on. So we have a force of 3I plus 8J, we have a mass of 0.5 kilograms. The question is simply, what is the acceleration? Well, irrespective of whether this object is at rest or not, if it's travelling at a certain velocity, then if you have a force of 3I plus 8J being acted upon it, it'll start to travel, or accelerate rather, in that direction. So, one way to deal with it, or probably the best way to deal with it, is to consider acceleration vertically and horizontally separately. Okay, so consider them as 2 separate things. So we want to find the acceleration. We'll use F equals ma as ever. We know that the force is 3I plus 8J, and that's equal to 0.5 times the acceleration. So the acceleration is 3I plus 8J divided by a half, which might look quite confusing, but we're simply going to work out the acceleration in the I direction and the acceleration in the J direction. So in the I direction, 3 divided by 0.5 is 6, and in the J direction vertically it's 8 divided by 0.5, which is 16J. So it's going to accelerate in that direction 6I plus 16J meters per second squared. So we can show acceleration in vector format as well as the forces. The second part of the question says find the magnitude and bearing of the acceleration. So now we're not representing acceleration as a vector, but we're representing it as the magnitude, the quantity of the acceleration, and the bearing. In other words, the angle from north. There's north. One way of doing it, the way the book does it, is to draw a triangle here, work out this angle using tan, and then to take that away from 90 for this angle. We can work out that angle directly, which is how I will do it. So if you want to see the 2 different ways, see how the book does it, see how I do it, and we'll end up with the same answers. So this, in terms of acceleration, if I now convert this into an acceleration diagram, this is 6 and this is 16. So I'm working out this angle here, which would be a bearing. So that's the angle, that's the opposite, that's the adjacent. So let's show some working here. Tan theta is opposite over adjacent, which is 6 over 16. So tan theta is 6 over 16. Theta is inverse tan of 6 over 16, which will give you an answer of 20.6 degrees. That's the bearing. The magnitude, which occasionally you'll see written like this, as modulus bars either side. The magnitude of that is simply using Pythagoras. Square root of 6 squared plus 16 squared, which should give you a value of 17.1 meters per second. And we ought to write down our level of accuracy here. That's to 1 decimal place. Okay, this is example 9. It gets slightly more complex here. We now have 3 forces, F1, F2 and F3, acting on a particle. The particle has a mass of 3 kilograms. Once again, for this particular example, I don't need an arrow coming down. Gravity is not part of this question, as it was in the previous one. Okay, we want to find out the acceleration of the particle. To do that first, I need to work out the resultant of these 3 forces. So F1 you are given as 2i plus 4j. F2 you're given as minus 5i plus 4j. And F3 you're given as 6i minus 5j. So there are 3 forces. I'm going to find out the resultant force by adding them together. So 2i plus 4j plus minus 5i plus 4j plus 6i minus 5j. So let's consider the i's first. 2 minus 5 is minus 3, plus 6 is 3, so 3i. Now consider the j's. 4j plus 4j, 8j, take 5j is 3j. So that is the resultant force. Force equals mass times acceleration. So 3i plus 3j equals 3 times by a, so the acceleration is, as we did before, just divide those 2 by 3, so the acceleration is 1i plus 1j. 3i divided by 3 is 1i, 3j divided by 3 is 1j. So we've got our acceleration here in vector form. If you're not sure what form to show it in, unless the question says otherwise, use the same form as the question. The question had vectors, force vectors written in terms of I and j. Write your answer in terms of I and j. If it had it in bracket form, so for example 2, 4 and minus 5, 4 and 6 minus 5, then write your answer in vector form, which would be 1, 1. If you're asked to work out the magnitude of this one, then obviously you could use Pythagoras. 1 across, 1 up would give you a magnitude of root 2. And because they're the same, it would be a 45-degree angle from x, which would also give it a 45-degree bearing. So that's the 4th part of Forces in Motion of Chapter 10.